In this lesson, we're going to use z-scores and probability that goes along with them to extend our idea, to learn some new terms, some new ideas that'll be very useful for us in our understanding of how statistics and probability works. So the first one we're going to talk about is the confidence interval. Well, actually, that's the overall idea for this lesson. So the confidence interval, statisticians use a confidence interval to express degrees of uncertainty associated with sample statistics. So I want to make sure that we're clear on what we're doing right from the start. So we all know that the inherent in probability is this uncertainty. If I say that there is a 70% chance of rain today, then I know that it might rain, but it might not. I'm suggesting that it's more likely that it's going to rain, but it's uncertain, right? So probability always has uncertainty built into it. So a confidence interval is a way of saying, okay, I think that such and such is going to happen. Maybe if I take a baseball game, maybe I am 90% certain that there's going to be between 10 and 15 hits in a baseball game. I'm just making this up off the top of my head, but just to give you an idea. So I'm giving this range of values, 10 to 15 hits, and I'm 90% certain that somewhere between 10 and 15 hits are going to occur in the game. That's the idea of a confidence interval. So I've given this range of values, and I've also given a percentage probability going along with it. All right, so that's the idea of a confidence interval. It's an interval estimate combined with a probability statement, and that was the example I just made up. So the interval estimate in that ad hoc example I just made was the 10 to 15 hits, and then the probability statement was the part where I said that it was 90%. Okay, so it's just so again, be clear on that before we go on. Everything hinges on your understanding of this. So it's a range of values of whatever we're measuring, and then a probability that something's going to fall within that range of values. For example, suppose a statistician conducted a survey and computed an interval estimate based on survey data. The statistician might use a confidence interval to describe uncertainty associated with the interval estimate. He or she might describe the interval estimate as a 95% confidence interval. So that's another one. I just used 90 in the example I did above. 95 means a higher confidence interval. So obviously the higher I can make that percentage, the more confident I am that something's going to fall within a given interval. This means that if we use the same sampling method to select different samples and computed an interval estimate for each sample, we would expect the true population parameter to fall within the interval estimate 95% of the time. Let's go back to my example that I made up a second ago, 10 to 15 hits. So let's say that I was able to be 90% certain that in any given baseball game there'd be 10 to 15 hits. What if I wanted to be more certain that, say, I wanted a 95% confidence interval? How would that change things? Well, if I want to be more certain that I'm going to have a given value fall within a range, it would stand to reason that I would need to make that range be bigger. So if I'm 90% certain that 10 to 15 hits would be the range for a baseball game, then maybe I would be 95% certain that 8 to 17 hits. So I might need to make that range a little bigger, right? Instead of 10 to 15, I make it 8 to 17, and then I can be more certain. I'm going to catch the different variables. Confidence intervals are preferred to point estimates and interval estimates because only confidence intervals indicate the precision of the estimate. So that would be the width of the interval. All right, so precision width of the interval. And the uncertainty of the estimate, that's the probability, that's the percentage. So I can play with either of these two conditions here, but you have to realize that they're connected to each other. So as I indicated just a minute ago, if I want to have a higher probability, then I'll have to have a wider interval. If I want to be more precise within a smaller interval, then that would facilitate, or that would cause me to need to have a lower probability of my values falling in there. So tied up with this confidence interval is margin of error. That's directly related to the precision of the estimate, okay? So it's connected to this one here, precision of the estimate. In other words, the margin of error, the way I create my interval is I pick a central point, and then I say, maybe I say that in a baseball game I expect there's going to be, on average, 12.5 hits. Again, average. I know I can't have half a hit, but let's say it's 12.5 hits. My margin of error, I'll say, well, maybe, it's going to vary a bit. Maybe they'll get another 2.5 hits more, maybe 2.5 hits less. Then I'll get my 10 to 15, but it's basing it around this central value I'm starting with. And the margin of error is how far above and below that central value I'm going to go. In a confidence interval, the range of values above and below sample statistics is called the margin of error. That's what I just explained. For example, suppose we wanted to know the percentage of adults that exercise daily. We could devise a sample design to ensure that our sample estimate will not differ from the true population value by more than, say, 5%, the margin of error, 90% of the time. Now, sometimes we do talk in percents, so that could be a little area of confusion. We have our 90% confidence level, but if we're talking, if our raw data is also a percent, we have to keep that separate, right? So this example was percentage, we're measuring percentage of population that exercises. So that means that our interval will also be given as a percent. So it might be, say, 60 to 70% of adults or a population exercises, and then we talk about 90% confidence in that interval. So be clear on the difference between the two. There's two ways to measure the margin of error that we just talked about, and it depends on what values we have given to us. Here's the first formula. E for margin of error is equal to z-score times the square root of p times p minus 1 1 minus p in brackets, which is really just q if we're thinking in terms of values we've learned before, over n. And again, all the variables are just explained right underneath here, as you can see. So E is margin of error, P is the probability of a statistic occurring, Z is the z-score of the confidence level, and N is the sample size. And again, 1 minus P is really just Q, the way we've thought about it before. Everything has to add up to 1 as far as probabilities. Think of it as success and failure again. Here are the main, in this table, the main confidence levels that we often go with: a 90%, a 95%, or a 99% confidence level. These are the z-scores that go along with them. You remember that we can use the z-score table to work backwards from a percentage to a z-score. And if we look at the z-score table right now, if I look at, say, a 90%, if I find 90% on here, that'd be as close to 0.90 as possible. That would be, it looks like about, where, it looks like about here. Sorry, Found it. All right, that looks like it's close to, about as close to 90% as you can get, right? That would mean that I would think that the z-score that goes along with it would be 1.28, right? 1.28, because I'd work backwards from that and get my z-score. If we look at the table, it's not 1.28, it's 1.65. And so that may be a cause for confusion, but it actually makes sense if you think about it. Our confidence level, this is based on a normal curve. If I have if I have a normal distribution that looks like this, right, there's my bell-shaped curve. If I want a 90% confidence level, we know we don't measure things really from one end normally. We're going to be measuring it out from some central mean, in fact. We're going to use the mean for this, not x squared, x bar. So we know that we're going to measure it this way and this way. So if we had a 90% confidence interval, that 90% is a chunk taken out of the middle, which means that the extra 10% would come from half on this end and half on this end. So if I wanted to find the z-score that goes along with a 90% confidence level, then I would want to actually find something that goes along with 95%, 0.95, or the z-score that goes as close to 0.95 as possible. So if we go back to that, get rid of this, and look for 0.95 or as close to 0.95 as we can. It's exactly halfway in between these two, isn't it? And if we go back, then we get 1.6, and then if we go up here, well, halfway between 0.4 and 0.5 would be 1.645, and lo and behold, that is the value that you can see right here on the table. So that's where it's coming from, this confidence level. So we want the z-scores that really we take half. If we were to look at the z-score table. Now, having said all that, we don't have to look at the z-score table. We can, if we're just going to use these ones, then we're fine using these ones. So you're going to refer back to this table. There we go, circled it, nice. We're going to keep referring back to this table, all right? But that was just a little of an explanation of where that came from. So that was the one formula. The other formula is this one, E equals Z times sigma, which remember is just standard deviation, divided by the square root of n. So we already know what E is. That's the margin of error. We know what the z-score is. That was just from the confidence level, from the table. We do know that n is the sample size. We don't use p in this case, though. If we don't know what the probability of a statistic is, but we do know the standard deviation, then we use this formula. And we'll see examples of both of these. All right, so let's just jump into a few examples. Lake Lavie, or pardon my French, pardon my pronunciation if I got that wrong, is one of the largest lakes in Algonquin Park. In 2009, 234 lake trout were caught out of a total catch of 911. So 911 fish were caught, 234 of them were lake trout. In 2000 and, let's actually get this highlighted. So 2009 I'll highlight in yellow. In 2012, there were 141 lake trout caught out of a catch of 689. Determine the percentage of lake trout caught for each year. Okay, so I'm going to just sort of separate this into two sections. I'm going to sort of do a double. Oh, I'm going to have to do 2 calculations for each of the next few parts, so I'm just going to draw a line down the middle so I can separate them. Alright, so we'll do 2009 on the left. So the percentage of lake trout, P, is there's 234 out of 911 caught, so that equals 0.257 or 25.7%. For 2012, we had 141 out of 689. So that's a a lower percentage. It's 0.205 or 20.5%. We can now calculate the margin of error using the first formula because we just calculated what P was. We're going to use a 95% confidence level, which means that I'll be able to get a z-score that goes along with that. We know what the sample size is in each case, 911 and 689 respectively, so I can get my margin of error. All right, so going back to, well, let's just write out our variables. Going back to the table, for a z-score for a 95% confidence level, I can see that it's going to be 1.960. But I don't need to write the 0 down. And then N for 2009 was 911. P I just calculated above. So my margin of error is going to be 1.96 times square root of P, which is 0.57, times 1 minus 0.57. I haven't given myself much room to write this, so get rid of the 0 there. 1 minus 0.257, extend that, all over 911. So, typing that in my calculator, making sure I follow proper order of operations, I get 0.028, or a margin of error of 2.8%. Doing the same thing for the 2012 catch, it's the same z-score, but because we're using the same confidence level, but N is now 689, and P is going to be 0.205. But I use the same formula, same z-score, and that works out to be 0.030 or 3%. All right, so now I've got a margin of error for each of these. Determine the confidence interval for each year. All right, so the confidence interval is going to be the average. Well, I guess this is going to be a percent, right? So this is one of these ones that we're going to calculate. The confidence interval is going to be given as a percent. So the percent that we came up with was 25.7. I could do this as a decimal as well, but I'll do it as a percent. So 25.7%. And the lower edge of this confidence interval is going to be, we're going to take away the margin of error from that. So use that, we'll use that, and we're going to take away 2.8%. The upper limit is going to be 25.7. 2.7%, but we're going to add the 2.8% to it. Again, this is what's giving us our range, right? When I do that, I get 22.9% as my lower, and I get 28.5% as my upper. So how do I interpret that? What that means is that I can be 95%, right? 95% confident that there were between 22.9% and 28.5% of the fish in this lake were trout. So again, we're given a range. So what we're measuring is the percentage of fish in this particular lake that are trout. We can't get an exact value for it, so we give a range, 22.9 to 28.5 in this case, and then we give our confidence that we're 95% confident based on the facts that that is true. Doing the same thing for 2012, we're going to now use 20.5% and 3% for our upper and, or for our center and then our plus minus. So 20.5 minus 3 and 20.5 plus 3. So in 2012, it ranged from 23.5%. Sorry, that would be adding now, wouldn't it? It ranged from 17.5% to 23.5%. Okay, so it's a different interval, different year. What happened? Did the trout change? I don't know. It's possible. First, let's look at, do the two confidence intervals overlap? Well, we have in 2012, let's just draw a line to represent 2012. I'll highlight it like this. Let's draw another line to represent, sorry, this should have been 2012. I'm off my game today. 2009, this one should have been. And then this one's 2012. Well, let's say this line just represents our interval. So the lowest value for this, oh my goodness, no, I do have it backwards. Apologies. I was doing it chronologically just to explain my error that I see now. I was thinking, well, of course, I put 2009 on the left and 2012 on the right because that's what I've been doing all along. But I have to look at my actual confidence intervals. So if I'm going to have a scale along the bottom, in 2012, it was actually lower values. And if you don't know what I mean, it should be clear in a second. Let me take the lower value here, this one. That's the lowest value we have, right? 17.5. And that went up to 23.5. And what I was going to represent with that is, a range. Our interval, it goes from there to there. And that was in the year 2012. Then back further in the year 2009, we had the range from 23.9 to 28.5. So that would be 22.9 on this scale would be, somewhere around here. So this was the limit here. This was 22.9%. And this upper limit was supposed to be 28.5%. The fact that I've used these two different colors, you can see the green on this, at least on my screen, hopefully it looks green on yours too, shows where they overlap. So really it overlaps between 22.9% and 23.5%. So this is overlap here. So if I want to give a specific example for, well, I'd pick any number between them, anywhere between these two numbers. Pick one. 23% is occurred in both years. 23.1%, 23.2%. Is it reasonable to conclude that the percent of lake trout has decreased from 2009 to 2012? It's possible, but no, we don't have to make that assumption. Because of the overlap, it's quite possible that the amount of lake trout has always been in the 23% range, and therefore it's been remaining stable. An opinion poll surveyed 100 households who were watching television at a particular time. Of these, 75% were watching Hockey Night in Canada. Determine the margin of error at a 99% confidence interval. All right, so we're going to have to go back to the table again. 99% confidence level was associated with a Z-score of 2.576. Of course, we want to fill in our margin of error formula, so if you want to remember or refresher what that was, we need either P or percentage, or we need standard deviation. There's no mention of standard deviation, so we do have P, so we're going to use P times 1 minus P. P was 75%. I'll do it as a decimal. And then over N, which was the population or the sample size anyway, it was 100. So we just plug everything into our formula. So 0.75, 1 minus 0.75 would be 0.25. That's an easy mental math to do. Put 100 here. Again, as long as we follow order of operations and everything is copacetic, we get 0.112 or 11.2%. So if we want to determine the confidence interval, it's going to be 75% minus 11.2% and 75% plus 11.2%. So 63.8% to 86.2%. So we can be 99% confident that between 63.8% and 86.2% of the population is actually watching Hockey Night in Canada. Just as an aside, before I answer part C, again, remember, the more confident we want to be, 99% confidence level, caused me to use a bigger Z-score, which of course then gives me a bigger margin of error, which then means that I'm going to subtract a bigger amount and add a bigger amount to the 75%. If I wanted to have a tighter interval, then I could go for a lower confidence level. Say I wanted just 90%, well then I would get a smaller margin of error and I'd have a smaller interval, right? So it's a trade-off again. How would a news source state these results? All right, so the percent of the population watching Hockey Night in Canada is 75% plus or minus 11.2% 99 times out of 100. Now, I don't know for certain that a news source would state it this way, but this is just another way of saying it. So you can give your central value, you can say plus or minus the margin of error, and instead of saying 99% confidence interval, you could say 99 times out of 100. If it was a 90% confidence interval, you'd probably say 9 times out of 10. And if it was a 95% confidence interval, you could say 19 times out of 20. So you just reduce those, change them to fractions, reduce them to their lowest terms. Last example, this is going to be an example of one that involves the second formula, because just skipping ahead, you can see it's giving us a standard deviation. So we're going to be using the other formula for this particular example. But let's backtrack to what it actually says. At the Uxbridge Fall Fair, masses of 8 giant pumpkins entered in a contest were, as given. Results from past fairs suggest that the masses are normally distributed, that's important, with a mean of 14.2 kilograms, all right, and a standard deviation of 2.5 kilograms. Determine a 90% confidence interval for the sample mean. All right, so if we want to use, I'm going to calculate my own mean here. So I'm just going to add all these together. The old-fashioned way. So we're going to add them all up. There are 8 pumpkins divided by 8. We'll get 13.6 kilograms. We want a 90% confidence interval. You may remember it, but let's just go back and look at the table again. 90% was 1.645 z-score. Let's put that here. N equals 8. And again, we're given a standard deviation of 2.5 in this case. So if we want to get our margin of error, the formula for when we have standard deviation is z times sigma over the square root of n. Notice how we don't take the square root of sigma. The square rooting is only occurring on the bottom in this case. So it's going to be 1.645 times 2.5 divided by the square root of 8, which works out to 1.45 kilograms. And that would make my confidence interval 13.6 minus, let's put the units here, 1.45. That would be my lower level. My upper one would be 13.6 plus 1.45. So my actual confidence interval is going to be 12.15 to 15.05. So that's my confidence interval. And again, I could say something like 9 times out of 10. I was just thinking, before I finish, the last thing I just want, in case this threw you off, because it sort of made me stop for a second. We were given this mean of 14.2, which I suppose, looking back at the question, maybe I was supposed to use that for my confidence interval instead of the 13.6. But it seems to me it were better just to calculate our own mean and work with that. If I made a mistake there, then we could make an easy adjustment just by adding and subtracting 1.45 from 14.2 rather than 13.6. But the math would work out the exact same, so don't worry about it either way.